Hi all, last day we have discussed matrix representation of a linear transformation from V to W, and V has a basis, ordered basis, say B, uh, consisting of the vectors alpha 1, etc., alpha n, and B prime is a basis for W consisting of the vectors beta 1, etc., beta m. Then the matrix representation of this linear transformation from relative to the basis B prime is defined as the matrix of the matrix Aij, and this is obtained by the formula T alpha j is equal to summation I equal to 1 to uh, m, this is Aij times beta I. So this is the coefficient Aij which constitute the matrix of T. Now we have in the theorem 11 we have discussed what is if we choose an alpha belongs to V, then this alpha can be written as x1 alpha 1 plus etc xn alpha n. Okay. Consequently, you can get T alpha is equal to using this argument. You can say that T alpha takes the form summation I equal to 1 to n, summation j is equal to 1 to, this is 1 to m, and j is equal to 1 to n a I j x j times beta I. Okay, so which shows that the coordinates of T alpha, the meaning of the statement is coordinate of T alpha relative to the basis B prime. How do you get this one? This is obtained by the expression T alpha is equal to linear combination of beta i's. Okay, because B prime consisting of the vectors beta 1, beta 2, etc., beta m. So from this expression, we can say that these are the coefficients corresponding to this beta I. So this is the matrix for j is equal to for this I equal to 1 to n. You can get that matrix. Okay, so that is equal to summation j is equal to 1 to n. The first one is a1 j x j. This is the first entry, and summation j is equal to 1 to n. A to j xj is the second entry, etc. The last entry will be summation j equal to 1 to n a, this is mj xj. Okay, because this contains exactly m entries, beta 1, beta 2, etc., beta m. Then we have m coefficients, that is this one. So this is obtained by, this can be written as the matrix A times x1, x2, etc., xm, xn. So this is equal to A times this x1, x2, xn is the coordinates of this alpha relative to the basis consisting of the vectors alpha 1, alpha 2, alpha n. Say the basis B. So this is the coordinates of alpha relative to the basis B. So this shows that, this equation shows that the matrix of this A is defined to be the matrix of T relative to the basis B prime. So from this you can write the coordinates of T alpha for any alpha belongs to B can be obtained using this matrix, say A times the coordinates of alpha relative to the basis, this is relative to the basis B prime, and this is relative to the basis B. So this is nothing but the coordinates of T alpha relative to the basis B prime can be obtained by this equation, that is this A is nothing but the matrix of T related to the basis B prime, and that times the matrix of the coordinates of alpha relative to the basis B. So this is the relation between the coordinates of an arbitrary element, vector alpha belongs to V, and the corresponding matrix. Okay, so from this you can say that if we have a linear transformation T is invertible, this is invertible, then you can get this T, there is a linear transformation U such that Tu is equal to identity. Okay, so this would imply that the matrix of T times the matrix of U, because the composition, the matrix of the composition is the product of the matrices of the individual linear transformations. So this will give the matrix of I. The matrix of I is nothing but the identity matrix. Okay, so which shows that this implies this matrix T is invertible. Okay, T is invertible matrix. Whenever a transformation is invertible, then the corresponding matrix is invertible. Okay, this is if you write this is a square matrix of any order, then T is invertible means this matrix is also invertible. On the other way, if we assume the matrix of T relative to the basis B prime is invertible, then we can say that this T is invertible. Okay, so in order to prove T is invertible, we need only to prove that T alpha is equal to 0 plus alpha equal to 0, or T is not singular because the dimensions of these two vector spaces V and W are the same. We can say that the one-oneness implies the onto-ness, and hence it will be the invertible linear transformation. So whenever T alpha equal to 0 implies this T alpha, the coordinates of T alpha corresponding to B prime is equal to A times coordinate of alpha relative to B equal to 0. If this is equal to 0, then we can say that the corresponding coordinate is equal to 0. If this coordinate is 0, we can say that this time is equal to 0. But our assumption is this is the matrix A is equal to A is the matrix of T, a matrix of T. Then this A is our assumption is this matrix is invertible, therefore A is invertible. Since A is invertible, so this equation implies that is A times this is the coordinate of alpha with respect to B, say x1, x2, etc. Xn equal to 0, where this alpha is equal to x1 alpha 1 plus etc. xn alpha n. Whenever this is equal to 0 and A is invertible, then the only possible solution of this system of linear equation is x1 equal to 0, x2 equal to 0, etc. xn equal to 0. So this would imply that each xi equal to 0 implies alpha equal to 0. So whenever T alpha equal to 0, we can get alpha equal to 0. Then if this T is linear invertible, then the corresponding linear transformation T is also invertible. So we can state these two concept as a theorem. That is the theorem. We can consider this as a result. T is invertible from V to W if and only if the matrix of T relative to the basis B prime is invertible or non-singular. Okay, so this is the theorem. Whenever T is invertible, then the corresponding matrix is also invertible. Okay, so this shows that the matrix and T have the same property. Now suppose T is a linear transformation from V to itself, V to V, and we have two bases, say B consisting of alpha 1 etc. alpha n, and there is another basis B prime consisting of the vectors alpha 1 prime etc. alpha n prime. Okay, then you can define the matrix of T relative to the basis B B and matrix of T relative to the basis B prime. Then what is the relation between these two matrices? Okay, so these are the representation of the same linear transformation relative to two distinct bases of V. Okay, so then these are two n by matrices. if the dimension of V is equal to n, and if it is defined over a field F. Then what is the relation between these two square matrices? Okay, that can be proved as these two matrices can be similar. That means this can be connected through a transition matrix P. So we recall the theorem 7 in the beginning of this chapter, the matrix of or the second chapter, theorem 7 says that whenever we have alpha and two bases B and B prime, then there is a transition matrix P. Okay, so that is equal to P times alpha relative to the basis B prime. Okay, so this is one equation. This is true for every vector alpha belongs to V. Okay, so this can be obtained using this alpha. This can be written as any alpha. Alpha prime can be written as alpha. J prime can be written as P11 alpha 1 P21 or P12 alpha 2 and so on. Okay, you can consider this equations for this is P1 J, or I will write it as this is obtained from the equation each alpha j prime is an element of V, and this alpha j prime can be written as the linear combination of alpha 1 etc alpha n. Then using those coefficients you can construct this. Okay, so we write these equations. Then the same thing happens for T alpha as well. Okay, then T alpha is again an element of V. Then T alpha relative to V can be written as P times this. Okay, that is equal to P times T alpha relative to this B prime. Okay, this happens because the same thing is true for any vector alpha belongs to V. Since T alpha is also an element of V, then the same thing happens. But we know that what is the relation between T alpha relative, the coordinates of T alpha are relative to the basis B and the corresponding matrix of T. Okay, so that is obtained by, if the matrix of T is represented by this B, we can say that T alpha B prime is equal to matrix of T times the coordinate of alpha for any alpha corresponding to this B. Okay, so this is what we have just proved, and these are the results comes from the results come from chapter 2. Now we write we combine these equations. We combine all these equations and write this matrix of T relative to the basis B, P times coordinates of alpha relative to the basis B prime is equal to P times coordinate of T alpha relative to the basis B prime. This comes from this equation because this is T alpha relative to the basis B because this is the matrix relative to the basis BB. Then there is a matrix of T relative to the basis BB. Then we use the same B here and this B here. So from this you can write T alpha relative to B is equal to matrix of T relative to B. You can avoid this, and then this is equal to, that is T relative to B times alpha correspond the coordinate of alpha with respect to B. This can be replaced from this equation. Okay, when you replace this as P times this, okay, so we can get LHS. Okay, from this you can write so that is this T alpha relative to B can be written as the matrix of T times B times this can be replaced by this equation. Okay, then you can get the LHS. So then the RHS of this equation will be the LHS of this. Okay, then what is the LHS of this equation? LHS is T alpha relative to B. Okay, so T alpha relative to B can be replaced from this equation, P times T alpha relative to B prime. So from the combining these four equations, you can get this equation, matrix of T relative to B times P times the coordinates of alpha relative to B prime, that is equal to P times the coordinates of T alpha with respect to B prime. Okay, this is the case. Now you translate this P inverse to the left, then you can get P inverse, the matrix of T relative to the basis B, P times the coordinate of alpha relative to B prime is same as coordinate of T alpha relative to B prime. Okay, so this is equation obtained from this by transposing P into the left. Okay, so what is the meaning of this? This shows that T alpha, the coordinate of T alpha relative to B prime can be obtained by some matrix times coordinate of alpha relative to B prime. Okay, this shows that this here what we have used here. Suppose we have a matrix like this. Say, suppose we have a matrix like D. Then you can say that the D is the matrix of T relative to the basis B prime. Okay, so the matrix of T relative to the basis B prime can be obtained by this equation. Okay, the coordinate of T alpha B prime can be written as that matrix times coordinate of alpha with respect to B prime. So this what we have written here is the matrix of T relative to the basis B prime. So that is nothing but this one. Okay, P inverse matrix of T relative to B P. Okay, which shows that the matrix of this matrix of T corresponding to or relative to the basis B prime and the matrix of T relative to B can be connected through an invertible matrix P in this way. Okay, that means if we put this is the matrix B and this is the matrix A, then we can say that B is P inverse AP. Okay, which shows that this B is the matrix of T with respect to some basis, and A is the matrix of the same linear transformation with respect to some other basis. So this can be connected through this P, okay, which shows that B and A are similar. Okay, so that is the idea. B and A are similar, which shows that corresponding to if you have two matrices corresponding to the same linear transformation, then they are similar. Okay, which is written as the theorem, the next theorem, that is theorem 14. If we have a finite dimensional vector space over the field F, let B and B prime are two ordered bases of V. Suppose T is Linear transformation. If P is equal to this is an n-by-n matrix with the column Pj is equal to alpha j, the coordinate of alpha j prime relative to B, then what does it mean? This means this Pj is the column vector, that is P1j, P2j, etc. P mj, nj. This is obtained. These coefficients are to be defined in such a way that can be obtained as the coordinates of alpha j prime relative to B. That means this alpha j prime can be written as P1j alpha 1 plus etc. Pnj alpha j alpha n. Okay, so the coefficients of the matrix P, the entries of the matrix P is defined in this manner. Okay, so this is what we have discussed in the, chapter 2. I hope that is in theorem 7. So using this idea, you can write this P, then that P can be considered as the transition matrix for the the two matrix representation of the same linear transformation. So the matrix of T related to B prime can be written as P inverse T relative to B times P. Okay, now you can replace this P as a matrix of some linear transformation if you define U alpha J. If you write U alpha j is equal to p11 p1j alpha 1 plus etc pnj alpha n. That means if you define this alpha j prime as the u of alpha j prime as the u of alpha j, then you can define a new linear transformation u. For this u, the matrix of u relative to the basis b is nothing but p. Okay, so this is a relation between the new linear transformation. So which shows that this equation can be replaced by this matrix of u is properly defined in this using this rule. Then matrix of t related to b prime can be written as matrix of u times matrix of t times matrix of u again. Okay, so which shows theorem 14. Consequently, we can define the definition of similar matrices, that is B is equal to P inverse AP, then B is called the similar matrix, the matrix similar to A. So the matrix similar to A is defined as P inverse AP. So this completes 3.4. In the next class, we will discuss 3.5 linear functionals.